Well, so let's finish off what we did on Wednesday. So if you've got a set, the collection of all subsets of U such as x minus u is finite, or is all of x, that is a topology called the finite complement topology. And where we left off last time was we noted that the whole set and the empty set are in that collection, and we saw that that if we had an arbitrary collection of non-empty elements of the finite complement, then their union would be there because of the De Morgan laws. So let's assume that each one of those is not empty or a whole set X. If it's empty, it's trivial. It doesn't do anything. If it's the whole thing, then X minus X will be finite. So this thing here is then a union, the union of that set. If you take the complement of that, by De Morgan's law, that's the same thing as the intersection of these things, but by the definition of the finite complement topology, these are finite sets, and the intersection of finite sets is finite.
Well, wait a second. That intersection is happening over a family that might be infinite, or?
But it doesn't matter because we've got finite sets. So even an infinite intersection of finite sets is going to be finite. Right. Yeah. So typically we only like our intersections to be finite, but the thing is intersections are smaller and smaller and smaller. So when it comes to finiteness, intersections don't bother. But when we come to unions, it does matter.
Okay. Yeah.
Right. But that's good because we want only a finite intersection. So this time we've got a finite family of non-empty subsets. And so when we look at the intersection of that finite family, okay, again, by the corresponding De Morgan's law, we look at the complement of that. And now this is now a finite union. And so this is a finite union of finite sets. And that's going to be finite. So the finiteness comes to all sorts out. Hello.
Hi.
Sorry, did you get trapped in the snow or something? It's just like, it's just a bugger to get around, isn't it? Okay.
Why is that union finite?
This union here is finite because it's a finite collection. So each one of these things is finite. And so a finite union of a finite collection is finite.
Well, I'm missing something here, but why is that union? Okay, it says finite family. Is that what we had wanted?
So
why do we assume that?
it's finite family because remember when it comes to topology, we're only interested in finite intersections.
Okay.
So this is a finite intersection, and so by De Morgan's law, the complement of a finite intersection is a finite union. Okay, the second example of the countable complement, that's one of the homework exercises, but it doesn't really differ that much from that thing there. Okay, let's. Okay.
Sorry.
Now we're studying the new. Are you okay now?
Yeah, I'm good.
Okay, good.
I'm sorry.
Because now I'm ready to start on the new stuff for today. Okay. So we've got a topology, and usually it's difficult to describe an entire collection. So we know that's a good thing in math when we're doing some sort of structure kind of thing, to have like a generating set. Hey, we're getting there. to have something kind of like that generates it, and that's good because quite often maybe a generating set will be easier to talk about, and what we want is a situation where we only have to prove things for the generating set that holds for the whole topology. So let's try that. So, so let's have the concept of a basis. So a basis for the topology on a set is a collection of subsets, which we'll call basis elements, such that for each element in X, there's at least one basis element containing X, that X. And if an element belongs to the intersection of two basis elements, then there is a third basis element such that X is in it, and that third basis element is contained within the intersection of the two basis elements that are given. Okay. So, to start with, that looks a little so what-ish, but we'll see that in a moment that this is actually a really, really useful concept. So, if our collection of subsets meets these two conditions, then we have a topology generated by this. So what are we going to do to give a topology? Basically, we've got to say what the open sets are, right? Because the elements of that topology are the open set. So a subset of our set is open if for any element of that open set, there is a basis element such that X is in that. Oh, that should be a little bit, I think. Yeah, such that X is in that basis element, and the basis element is contained within the open set. Okay, so there's two things to note. Firstly, each basis element itself is open in that topology. So that's an element of T. And if you look at this thing, it's pretty vacuous, right? Why? So if we've got a basis element B, why is that open? Well, if X is in B, then there is an element B, i.e. itself, such that X is in B and B is contained within B. So vacuously, basis elements are open themselves. Okay. More importantly, is the second note is that this collection of open sets is in fact a topology. I've called it open. Is it really open? Remember, the real definition of open is that it belongs to a collection of a topology. Okay. So we've got to show that that collection is a topology. So that's what we'll do next. Okay. So recall, this is how we're defining an open set. Okay. So what do we need for a topology? We need the empty set to be in there. Well, the empty set is vacuously open, right? Because for every element of the empty set, whatever condition you want, doesn't matter, right? Because there are no elements in the empty set. So the empty set is vacuously in the topology. Almost as trivially, X, the whole set itself, is open. Why? Because for every element in X, if you remember U now is our whole set X, there is a basis element such that X is in that basis element and B is contained within X. Okay, well, by our definition of a basis, that indeed holds. So So it's the other two conditions that are actually, we've got to actually work on a little bit. I don't think we actually have to work that hard at all. So where am I up to? Okay, so what we've got to do, we've got to show that arbitrary unions of elements of T lie in T. Okay, so arbitrary unions of open sets are open. Okay, so let's start off with that. Okay, so here is the set that we want to show is open. So let's say we have an element in that set. Well, if X lies within a union of things, that means there exists an alpha such that X is in a particular U alpha, just by the definition of union. So, but this is an open set, so there is a B then, such that X is in B, and that's contained within U alpha. But U alpha is contained within that union of all those sets. Okay, so that shows us that that union is open. That's all we had to do for that. Lastly, we have to show that finite intersections of open sets are open. So again, so what we'll do then is induction. So let's have a look at the case n equals 2. And let's say that we're given two sets U1 and U1 and U2, which are in that collection T. I really don't know how to do a split T. What do we want to show? We want to show that U1 intersection U2 is open. Okay, I'll just use the word open rather than trying to embarrass myself with it, talking about a T. Okay. So now what we do is we actually use condition 2 of the definition of a basis. And by that, we see that so what do we got? We want to show this is open. So let's say we have some element in that intersection. Am I in the way? I feel like I'm in the way all the time. So we have an element in the intersection. So that means X is in U1 and X is in U2. So that means that X is in some B1 and X is in some B2, where they're basis elements. Okay, and so by condition 2 from before, if we've got, so that means that there exists, so by condition 2, there exists a B3 such that X is in B3, which is contained within B1 intersected B2. So that tells us then that U1 intersected U2 is open. And then for the induction case, we want to show it for the case N, given it's true for the case N minus 1. And so then if we look at U1 intersected U2 intersected U, intersected, what is it? Intersection. Intersected UN minus 1, intersected UN. What's the trick that we do? How can we write this? So it's true for n minus 1 that the intersection of n minus 1 things is open. Will, what do we do?
Well, then you just got two sets there on either side of the last intersection. And you can do what you've already done.
Right. So this is open by the induction hypothesis, and the case n equals 2 satisfies. So we've reduced this to 2 open sets, and we've already proved that. Okay, so this tells us that this is indeed a topology. Excellent. So let's have a look at a few examples. So I'm just here recalling, remember this is a definition of a basis. And this is what we take from this then to be the definition of an open set given this basis, and we know that that's a topology. So let's have a look at the discrete topology. So I claim that the collection of all one-point subsets of X is a basis for the discrete topology on X. Okay, let's go through the conditions to double check that this is indeed a basis. Okay, for each element, there has to be at least one basis element containing that. So given an element given X, an element of X, what's the basis element containing X? It's just, so X, the set containing X, right, does the job. Okay. Secondly, if X belongs to the intersection of two basis elements, then there is a third basis element. Okay. What about this one? So if X is an element of B1 intersected B2, what does that tell us about B1 and B2? They both contain X, so what does that mean about B1 and B2? Yep, because B1 has to be the set X, B2 has to equal the same set X. So B3 equals the same set X. So sometimes when you prove these things get very tautological. It's just, set X is the set X or whatever. It can get quite funny at times. Okay, and what is an open set? Let's just go through. So what is an open set in the discrete topology?
Any subset of X.
Yeah, so a discrete topology is that any subset is open. So let's check that any subset is open. A set is said to be open if for every x in that subset there is a basis element B such that x is in that basis element. Sorry, that should be a normal B, not a script B. So x is in that set and B is that. Well, that's true, right? Because any arbitrary set is made up of singletons, and each singleton is a basis element. And that basis element is then contained within that whole set. So again, it's sort of vacuously true. Okay. So it might not be a very interesting example, but at least it kind of shows us how we can go about using these conditions. So let's do something a little bit more interesting. So let's have a look at a plane R2, and here is two topologies that we can put on it. Okay, so let B be let our basis be the collection of all interiors of circles. Okay, so here is R2, and so a subset U is open if every x in U lies in some circular region contained in U. So what does this mean? Okay, so let's go back to the definition then. Okay, so it's a basis. So why is it a basis? Okay, so given any point in R2, we can put a circle around it, and it's going to lie within that circle. So it satisfies condition 1. What's condition 2? Condition 2 says if x lies in the intersection of two basis elements, then there is a third basis element contained within that intersection. Okay, so what's the picture there? So we've got an x, and let's say that it's contained within two within two basis elements. So here's one circle, and here's another circle. So why is there then a third basis element?
You can always take a radius small enough to fit in that.
Exactly. And that's basically the proof. You can write it up, but you know, this is B1, this is B2, and this is B3. You know, you have to, what do you have to do? You have to say, you know, what is the distance x from B1, the boundary of B1, and x is the boundary from B2, and let delta be less than the minimum of those two distances, and look at the circle centered at x around that, and that'll do the job. Okay. Second one. Let B prime be the collection of all interiors of rectangles whose sides are parallel to the axes. It is a basis for a topology. Here a subset U is open if every x in U lies in some rectangular region contained in U. Okay, why is it a basis? Firstly, every element has got to be contained in some basis element. So if I give you an x, then you just put a rectangle around it. You do the rectangle from, I don't know, from x minus 1 to x plus 1 and y minus 1 to y plus 1, whatever. You can actually write down what the things are. What's the second requirement? The second requirement is if it lies within two basis elements, then there is a third basis element that lies within the intersection. Actually, this one is easier than the previous one, right? Because the things are parallel, the intersection is actually a rectangle. Here's B3. And so the intersection is either going to be empty or it's going to be a rectangle, and if it's a rectangle, then it's a basis element. Okay, so this gives, here we've seen two topologies on R2. Actually, it turns out that it's the same topology. Okay, and the next slide will do a useful lemma, which will be able to prove that that's actually the case. Okay, because to start with, you might think, well, how would we prove that? So that's why we have the next collection of lemmas. So these are some lemmas which are really kind of workhorse kind of lemmas that you're going to use to actually prove things. Okay, so we've already given, one sort of definition of a basis. Where was it? Oh, here. Okay, and we proved that this will then give us a topology. Here's kind of like a little bit of a simpler one. So this is, so if we've got given a set X and we've got a basis for the topology, so we've got some basis, then the topology equals the collection of all units of elements of that basis. And these are arbitrary unions. Okay, so for example, the one before we saw with R2 with the circular regions. So open sets are then any arbitrary union of little circles gives us an open set, or any arbitrary collection of rectangles. Okay. Now, we call it a basis, but it's not a basis like you know from linear algebra, because bases generate things in linear algebra. What's the other condition that you have to have for a basis?
There's only one way to write it.
Right, it's linear, linear independence is an important thing. So there's a unique way of writing anything in terms of a basis. This is not true in topology. So, like in the previous example, we're going to claim that those two topologies are the same. So there's lots of ways in which you can describe an open set as a union of disks, and there's lots of ways that we can describe an open set as a union of rectangles. It's going to turn out they're both open sets, and these bases are completely disjoint, right? Rectangles and circles are different things. So that's as ununique as you can possibly get. Okay, so why is this true? So I want to claim that this topology T equals the union of arbitrary unions of basis elements. That was a slightly better T. Okay, so if we want to show that two collections are the same, the typical way is you show one contains the other and then the other contains the other. So all we've already seen that all basis elements are themselves open sets. And since we're given that it's a topology, T is a topology, the union of elements of T are going to lie in T. So this is kind of fairly straightforward, since B are actually open sets themselves, and unions of B lie in T. Okay, so this collection definitely lies within that topology. Let's go the other direction, the converse direction. So let's say we have some open set. So for each element in our open set, we can choose a basis element X such that X is contained within that basis element, and that's contained within U. That's by definition. So then U equals the union of all these basis elements. And these things lie within B, so therefore it lies within that. So if we've got something in that, it lies in that. And so that's done. So that's really how you should be thinking of a basis. So you've got some collection, you're going to think of a basis, and open set are just going to be arbitrary unions of that basis.
If you have two different bases for the topology, can they have differing cardinalities?
The bases?
Yeah.
I think so, because, for example, for the real line, you might have, I think you can get away with intervals which are rational. I think that gives you a basis, and that's countable, and then you can have just an uncountable one, just like being too, adding too much.
But the cardinalities of the script data, rather than, because how many, it's a question of how many open intervals you would have, right? And not the sizes of the intervals themselves.
No, but like if you have Q cross Q, it's countable, right? And so you look at all A, B, such that A and B, that would be a countable basis for the real line, wouldn't it?
Are those open intervals?
Open intervals, yes.
As subsets of the reals, or with all the irrationals removed?
So this would be a basis for the real line, for the reals. In the standard topology.
Okay.
Right? Because it's like an interval like e to pi is an open set, and you can have that as a countable union, because you can have a sequence that of rational numbers that goes towards e or pi.
In the text, they define it with uncountably many open intervals. So you're saying you do the same thing with discountable many?
I think so. I think that might be an exercise. That's the point. So, but then if you're going to talk about a minimal basis, whether that has the same cardinality, I don't know. Okay, the second thing, useful lemma. So this is always going from so previously we've just gone from a basis to a topology. Sometimes it's useful to go the other way, so that if we're given a topology, can we pick out a basis from it? And the answer is yes. So if you have a topological space and we have a collection of open sets of that space, such that for each open set U of X and for each element of that open set, there is an element of that collection such that that element is in our C, which is in our collection, is contained within U. And if you can do that, then that collection C turns out has to be a basis. Okay, so let's actually show that. So we want to show that C, script C, is a basis. So we've got two conditions to satisfy. This is easy, right? Because since we've got a topology, X is an open set. And so by the hypothesis that we're given here, if we're given an element X, then it has to lie in some C in that collection, and C is contained within X. Okay, so one is fairly trivial because X itself is an open set. What about the second thing? What do we want to do? We want to show things about intersections. So let's say we've got some element that lies in the intersection of two elements of our collection. So C1 and C2 are open sets given, so that means C1 intersected C2 is an open set. So by the hypothesis then, there exists a C3 such that X is in C3, and that's contained within C1 intersected C2. Okay. And there's still one third thing left to prove. Okay, we've shown that C is a basis, but what haven't we shown? So we're missing one thing. Exactly, right. We've got it as a topological space. So remember when we talk about a topological space, there's the set X, and there's also T that goes with it. So we've shown that C is a topology. We just got to show it's the same topology as the one given for X. So let's say we've got X is an element of U, which is an open set in our topology T. Then the hypothesis says then there is a C in our collection such that X is contained within C, which is contained within U. So that means U is an element of the topology generated by C. I'll just make up that notation. All that. So any open set in T is an open set in the topology generated by the basis C. And then conversely, if W is in that as an open set in the topology generated by C, then W equals a union of various elements of C alpha, could be arbitrary, by the lemma up here. That the topology generated by that basis is just equal to a collection of unions of elements of that. But since each C alpha is open, this is actually an element of the topology T. Since the C's are open themselves, an arbitrary union of them is also going to be open in T. So the two topologies are the same. Okay. The next useful lemma is a lemma for comparing topologies. That's a really useful thing to do because it'll help us to compare topologies. It'll be useful to prove things are the same. Two topologies are the same, right? Because the standard way to prove two things are equal in this kind of situation is to show that each contains the other. So let's say you have two bases for different topologies, supposedly different topologies, on the same set X. Then the following is equivalent. T prime is finer than T. So remember what finer means. So finer means like if you've got one topology and you think of the set somehow being broken up into pieces, being finer means you take those same pieces and you break it up even more. That's where the finer comes from. It's like going from, pebbles to sand kind of thing. It's actually taking those pebbles and then breaking them down further. Okay. So T prime is finer than T. It's the same thing as for each X in our set and each basis element of B from this topology containing X, there's a basis element B prime from that other basis such that X is in that basis element which is contained within that basis element. So this whole idea of taking something and breaking it down into something finer. It's finer if you've got something that's in a basis element that you can find a smaller basis element from the other basis set, then that topology has to be finer. Okay, so let's prove that. Okay, so let's show that 2 implies 1. if this is the case, then T prime is finer than T. Okay, so how do we do that? So if we got U, an open set in this topology, then T prime is finer if we need to show U is also an element of T prime. So that's what we need to do to show that it's finer. Okay. So let's say X is an element of some of our open set here. So therefore there exists a B from the basis that generates T such that X is an element of B is contained within U. But by 2, we've got that X is an element of B prime, which is contained within B. And that's contained within U. So that tells us that U is an element of that other topology. Okay, so if 2 holds, then any open set in T is also going to be an open set in T prime by this condition, since we could have basis element contained within another. Okay, why does 1 imply 2? So let's say X is an element of B, where X is some element of our set and B is some element of our basis. B is an element of the topology T, but T is coarser than T prime, so T is actually contained within T prime. And T prime is generated by B prime, so therefore there exists a B prime such that X is going to be in B prime, and that's going to be contained within B. Okay, so now it's a simple thing to prove that the topologies on the previous slides are the same. And to do that, all I need to do is do a picture. Is everyone finished with this? So all we need to do to show that one topology is finer than another is to be able to squeeze a basis element between an arbitrary basis element of the. Okay, so for example, here is a an arbitrary basis element of the circular kind. Okay, and so all we've got to do is show that there is a rectangular region containing X within this. Well, that's straightforward. And you can go through all the details, but that's fairly straightforward. So any circular basis element contains a rectangular basis element, and that's true for all points within that thing. So this shows that the rectangular basis is finer. The topology of the rectangular basis is finer than the topology of the circular basis, but if I have a rectangular basis element and I pick some arbitrary point x there, I can put a circular basis element inside that. And that tells me that the topology generated by the circular basis is finer than the topology generated by the rectangular basis. So therefore, the two topologies are the same. And really, the only hairy details is actually doing the actual geometry and algebra to actually write down how to go about doing that. I think we need to bother about. Okay. And I believe we have come to the end of today, haven't we? Okay. I know where to start off next time. And I'll stop recording.